Hello and welcome to VEX Robotics for Competition, a tutorial for new teams, presented by McCallum Robotics of Austin, Texas, Team 8756. This portion of the tutorial will cover time-based line-by-line autonomous programming. The code is going to go here in the autonomous section, so everything we run in here will be executed during the autonomous period of the match. And just like we saw when we were programming for driver control, where we want to give ourselves a reference in comments of what we need to do, autonomous, we're going to want to do the same thing. We're going to want to imagine the game and our robot's capabilities, and then write out the steps that we want our robot to take in plain language using comments, and then we can expand on that to have it actually do motor functions in code. So I might want my robot to drive forward for, say, 20 inches. And then I'll have it pick up the ball. Things like that. So I know what my scoring object is, I know what my robot can do, I can give it some instructions. So I've written out a few more in here. So we're driving forward, picking up a ball, turning right 45 degrees, driving forward again while raising the arm in the lift to, say, go for a goal, and then we score the ball and back up and reset everything so it's sitting on the ground. So that's the plain language way to do it, and how we're going to actually code that is we're going to give motor instructions. So we're going to tell the motors to spin at a certain power, and we'll tell it to spin for a certain amount of time, and that will make it do these steps. So we've already done motor instructions. We had down here where we have them mapped to our signals, but if we just put a number here, that would be an instruction to go at a certain power. So we've done this before, we'll do it again. We want to set the motor, and we'll say drive front, because these are the drive motors we want to affect. And we'll just set it equal to, how about full power, 127. We need to give that same instruction to all four motors if we want it to drive forward. So we want to do the left back, right front, and right back. So now we have it driving forward. In order to get it to go 20 inches, we're going to have to guess. We're going to have to have it go for a certain amount of time and fine-tune that amount of time until it's 20 inches. So I'm looking over here in my options. I've got timing, and there's commands and variables. And if I'm new to this, I really don't know which one I want to do. You can mouse over and get some clues, but this is a great time to check the help and look in that same area in help so that there'll be more description. And there's timing functions. And I can find out that there is a clock running on the VEX Cortex, and it runs in millisecond increments. There's timers, like stopwatches, and then there's some information about how much data you can store within those variables. And there's a description, a better description of every one of these items over here. So there's a way to clear the timers, so that's like resetting stopwatches for T1, 2, 3, and 4. There's a clock that runs based on the Cortex's time. There's a clock that runs based on how long the program has been running, like when you first start it and it syncs up, that's when the program starts. There's a clock that runs that is whenever the Cortex is powered on. So you might reload the program several times, but this clock will stay going as long as the Cortex isn't reset, like power cycled or has a failure. There's time 1, that's a way to call those stopwatches. So none of these so far are going to let us set a motor time. Time 10 and 100, those are also stopwatch functions. Here's a wait function. And it says program execution will wait for a specified number of clock units. All right, and this is 1 milliseconds, and another option is 10 millisecond units. This is the one we want because this is going to have it pause while the motors are running. I can see if I read this further that the 1 millisecond is a timer that will last 32 seconds at the most. And if we went to 10 milliseconds, it would last 327 seconds. So this is probably fine for what we're doing. We're not going to wait very long. If we had to wait a really long time, we would want to have a longer wait time. So now we know what we're looking for. We want to use the wait 1 ms. So I'm going to go down here and I'll just go ahead and click this guy over, and it's going to need a parameter of time. Not sure how long it's going to take it to go 20 inches, so I'm just going to say 1,000, which would be 1 second. And it may seem like we're done because we're told it to drive forward for 1 second. But the default position of the motors is not 0. It isn't going to just go back to 0 unless we tell it to. So if we did wait 1 second while these are running and then went to the next step, the drive motors would keep running no matter what we told the rest here. So we need to tell it to stop all those motors too. So I'm going to copy and paste those and give them some zeros to have it stop. So this is what our first test will look like. We're going to drive forward full power for 1 second and then stop. I'll download that and we'll see how it does. So I'm downloading my program, just hitting F5, and the default portion of the competition template that gets run when you're in this debug mode is the driver control. And we want to look at the autonomous. So I need to go into, where do I need to go? Here we go, Robot, debugger window, and I want to show competition control. And then that will let me choose which section to run. So I want to click autonomous, and then I can click start, and that will actually run the autonomous. That was surprisingly close to 20 inches, and for the purposes of this tutorial I think we can leave it there and say that that was 20 inches. What you would really need to do though is find out exactly with a measure with the tape how many milliseconds you needed to run. So I could really make this comment line a little bit more descriptive by saying run the drive motors at 127 for 1 second. And that will be useful to me later on when I'm trying to make estimates of how much I need to drive. Now I want to go to the next step, which is pick up the ball. So I'm going to say that my flag twirler is what picks up the ball. So I need to give a motor instruction to the flag twirler. So that would be motor. And flag twirler. And I'll say positive 127 is what picks up the ball. And then I need to give it a wait. Let's say it takes a second to pick up the ball. And then I need to turn the flag twirler off. So I can add that. I'm pretty confident that'll work. It's just turning one motor and it's not having to do anything else. So turning right 45 degrees, that's going to be our drive motors. So drive motors, and let's see, I'll need to do all 4 motors to turn, and I need to have a wait, and I need to make them stop. So this is all going to be similar. I need to turn if I want to turn right, I need to turn the left motors forward and the right motors backwards. And I know from experience that I probably don't want to give full power, because that's actually really fast when both motors are working opposite of each other. So let's do 80s. And I will say 45 degrees is not very far. Let's say a half second, so that would be 500 milliseconds, and then they all stop. So I'm going to download this and test it, and we'll see how it does. It's going to drive forward 20 inches, twirl the flag for a second to pick up an imaginary ball, and then turn right about 45 degrees, we'll hope. Well, it drove forward, twirled the flag, and turned, but it turned further than 45 degrees. Let's reduce this to just, say, 250, about half, because it seemed like it turned 90. And then I'll try again. So just looking at it, it looked like it turned slightly less than 45 degrees there. Didn't have any tools out, but that's just a decent guess. And I remember the last time when I did a half a second, it turned a little bit less than 90 degrees. So I'm going to put down an estimate that this is turning approximately 15 degrees for every 100 milliseconds at 80 power. And that way I can better guess my turns later. I am going to say that if I turn it at 45, I'm probably going to run out of room on that small mat I had. So I'm going to just say I want to go 60 degrees. And 60 degrees would be, with this approximation, 400 milliseconds. And that would be 40 or 0.4 seconds. And now I want to move on to the next step, where I'm trying to do multiple things at once. So I want to run different parts of the robot all at once. So I know I need to see, I'm moving forward 8 inches, raising the arm 5, and running the lift. So moving forward, well, that's just our good old drive function. And we've got that there. And thinking about my estimates, I did about 20 inches in a second. So I'm going to do about 400 milliseconds if I run at full power. And I'm not sure if I'm going to be able to get my arm up fast enough in that time period. So let's plan on moving a little bit longer. We'll plan on moving for a full second. So I'm going to need to use some sort of lower drive power. Let me get everything in there and then we'll think about the amount of time for everything. I need to get my arm motor functions in. And so that was arm, left top. Let's do the arm at full power because I want it to move up pretty quickly. I'll need to make 4 statements for the arms. Left bottom, right top, right bottom. And then I need one more motor statement for the lift. That'll be lift. So I'm starting these guys. If I want the arm to go up about 5 inches, say, probably need it full power for a second. We'll see. And then that means I need to drive slower to make all this work out. So whenever you're using multiple things at once, you'll need to juggle between the amount of time and the amount of power given to each part so that they all arrive where you want them to in this time allotted. So I'm going to put my drive motor at let's say 90. I'll just be intuitive about it. I'm sure I could do a little bit of math there and be better, but we'll do it that way. And now I need to stop all these guys. So let me copy over all those motor statements. Put the drive to 0, lift to 0, and then the arm, remember we need to do 20s so that it stays up versus gravity. We'll test that and we'll see what we got. That was reasonably close for what we're doing here. Obviously when you have actual scoring objects and actual field parts, you'll want to iterate until it's really right. I'm going to have it turn just a little bit more so that it doesn't run off the mat. So I'll go say I'll turn 75 degrees, which would be more like 500, more or less. And then we'll add our remaining statements, score the ball. Well, that's just the same as this flag twirler here, but reversed. So let me copy those guys down. And just do a negative. So if I picked it up going positive, I'm putting it out going negative. And now I want to do a function that backs away and resets everything. So I want to run every motor that I did up here but do it backwards. I just want to kind of pull the bot away from the imaginary goal. So it's really the same as this thing, except for I'm backing up. I'm lowering my arm. Remember, we want to lower at a lesser speed than full power so that it's not overwhelmed by gravity. And then my lift, I'll take it down, and then everything will be set to 0 again. So this will sort of reverse this step that was up here and have it back away from the goal. And that'll be the end of our program. Let's see how it looks all together. So there we have a simple 6-step program. There are a few last things to do to make it useful going forward. So here I was figuring out roughly how well it turns. Giving yourself those estimates is really important to making other programs. So if I move this up to the top and kind of create a comment area up at the top of my autonomous section that has time estimates, and I can put a few lines that address the different types of drive and give an estimate to base it on. And the best way to do these is actually to create simple programs where your bot, say, drives for 3 seconds, and you measure how far it drives at full power. And you do that several times, and you can get a pretty accurate measurement of how far it drives per unit of time at full power. But I can just put down an estimate that it drives approximately 2 inches per 100 milliseconds at 127, because that's roughly what we noted from before. So I can add some estimates like that. Another thing to do is to add some more comments to each of your functional areas. So here we've said what the whole step is going to be, and I can add a little bit of comment to say start the drive motors and wait 1 second. And if this seems like busy work, that's kind of too bad. The problem is if a new person comes to look at this program, they won't be able to read it as well as the original author. So you want to have a lot of comments in there so that it's easier for somebody to pick up where you left off and build their own program later on. It may be somebody this year on your team, it may be next year. So adding some good comments is good. And then I know I'm going to have more than one program because there's 4 starting positions in Vex competition, 2 for each color. So it's likely I'm going to have multiple programs, and you can see these start taking up a fair amount of space in the document. And so being able to page through the document and find the right program is going to be important. So I'll want to add a nice header that can tell me which program I'm actually looking at. So I'll say start program 1 red zone score, something like that. So I know which program it is and kind of what it does, and I can do an end for that down at the bottom. So that would look something like this all put together. I've got a time estimate that talks about all the different areas of my build. I've got a clear definition of which program I'm looking at while I'm starting it. I've got comments all the way down about what every line is doing. I've added some notes to every one of the beginning of every one of the lines of action to say what it's going to do and as I say, clarified it, and then show an ending to every program. One final note about autonomous programming is that you may not have a field to program on, but that is okay. You can still build your autonomous program using these line-by-line steps because you can diagram out your plan, and you can give good guesses at your time and speeds for each step. You can also tape out an area on any floor large enough and test your robot on that floor. The day of the competition, there will be a practice field available, and you can take your bot and your computer and you can set up near the practice field right at the beginning of the day and fine-tune the steps that you've already laid out. And if you're lucky, there may be another team in the area that has a field that they keep set up, and you can take your program maybe a day or two in advance and fine-tune it on their field so that at the day of the competition there's a little less stress. But don't think that just because you don't have a field, you can't make an autonomous program. You absolutely can. Our team has done it and done it successfully. Thank you for watching.